Section 1.7, I'm sorry, section 1.6, calculating limits using the limit laws. So we're going to use those limit laws from section 1.7. Note, it looked like we kept doing the same thing over and over again. And the reason is because we really did. So let me give you a lemma. A lemma is a small theorem. It's a theorem used to prove a bigger theorem. So in the process of proving some theorem, all of a sudden you're like, oh, I could do this if I knew this. And so that's what a lemma is. It's that other fact that you need in order to prove your big theorem. So we could have proven all those statements from section 1.7 using the following lemma. Suppose epsilon is greater than 0. We have the following. X minus a in absolute value less than epsilon over 2, and y minus b in absolute value less than epsilon over 2 implies that x plus a minus the quantity a plus b in absolute value is less than epsilon. Note that we use these facts to prove the sum of limits is the limit of a sum is the sum of the limits. And the difference, the limit of a difference is the difference of the limits. X minus a in absolute value less than the minimum of 1 over epsilon divided by 2 times the quantity absolute value b plus 1. And if absolute value of y minus b is less than epsilon over 2 times the quantity absolute value of a plus 1, then absolute value of x times y minus a times b is less than epsilon. If you look here, this is what we used when proving the limit of a product is a product of the limits. Next, if b is not equal to 0, and if y minus b in absolute value is less than the minimum of 1/2 absolute b and epsilon over 2 times absolute value of b squared, then y is not equal to 0, and 1 over y minus 1 over b in absolute value is less than epsilon. So what you notice here is that this is what we use to prove, well, the reciprocal and the quotient. The limit of a reciprocal is reciprocal of the limit, and the limit of a quotient is the quotient of the limits. So let me try to prove this. Okay, so let me try to prove this. So let's look at this guy. So let's start with this. Let's start with this and see if I can show this given these. So let's write this down. So the absolute value of the quantity x plus y minus the quantity a plus b, all in absolute value, is, well, again, let's group the x's and the a's, the y's and the b's. So this is equal to the absolute value of x minus a plus y minus b. By the triangle inequality, this is less than or equal to absolute value of x minus a plus y minus b. But by assumption, absolute value of x minus a is less than epsilon over 2. Absolute value of y minus b is less than epsilon over 2. So each of these are less than epsilon over 2. And so this whole thing is less than epsilon. And that's what you wanted to show. No, I'm not going to prove this other one. Okay, so next time we'll prove the rest of this. Actually, I'll probably prove the whole lemma yet again. So next time we'll prove this lemma and continue on with section 1.6. Any questions about anything? Any questions? Okay, if there are no questions about anything, then that's it for today. And I'll see you guys tomorrow. Remember that for the summer session, we have class Monday through Friday. So we have class on Friday. Okay, I guess I'll see you guys tomorrow then. Hey, bye-bye now. Since absolute value of x minus a is less than 1, it's the minimum. And so it's less than 1. Then absolute value of x minus the absolute value of a is less than or equal to the absolute value of x minus the absolute value of a in absolute value, which by the triangle inequality is less than or equal to x minus a in absolute value, which by assumption is less than 1. Therefore, adding absolute value of a to both sides of your equation, of your inequality, the absolute value of x is less than absolute value of a plus 1. Therefore, xy minus ab in absolute value is equal to, just adding and subtracting, xb is equal to xy minus xb plus xb minus ab, all in absolute value. Grouping the first two terms and the last two terms and factoring out what's in common. Well, what's in common in these first two terms is x. What's in common in these last two terms is b. Therefore, this is equal to x times the quantity y minus b plus b times the quantity x minus a, all in absolute value. By the triangle inequality, this is less than or equal to absolute value of x times y minus b in absolute value plus the absolute value b times y minus times x minus a in absolute value. Well, we have that absolute value of x is less than absolute value of a plus 1. And by the assumption of the part 2 of the lemma, y minus b in absolute value is less than epsilon over the quantity 2 times the quantity absolute value of a plus 1 plus the absolute value of b. And by assumption, x minus a in absolute value is less than epsilon over the quantity 2 times the quantity absolute value of b plus 1. The absolute value of a plus 1 cancels. And so this is equal to epsilon over 2. Since absolute value of b divided by absolute value of b plus 1 is less than 1, then this whole quantity here is less than epsilon over 2. Therefore, this is less than epsilon. And that's what you wanted to show. Next. since y minus b in absolute value is less than 1/2 times the absolute value of b, then absolute value of b is equal to adding and subtracting y. Absolute value of b is equal to b minus y plus y in absolute value by the triangle inequality. This is less than or equal to b minus y in absolute value plus absolute value of y. Again, changing the sign of what's inside the absolute value does not change the value of the absolute value. And so this is equal to absolute value of y minus b plus absolute value of y. And well, we know that the absolute value of y minus b is less than 1/2 absolute value of b. I can subtract 1/2 absolute value of b from both sides of my inequality. So I have that absolute value of y is greater than 1/2 absolute value of b. Absolute value of b is greater than or equal to 0. And so 1/2 absolute value of b is greater than or equal to 0. Therefore, y in absolute value is greater than 0. And so y is not equal to 0. Since y is not equal to 0, I can divide both sides of my equation by the absolute value of y. And since b is not equal to 0, I can divide both sides of my equation by the absolute value of b. And so I can take the reciprocals. So I have that 1 over absolute value of y is less than 2 over the absolute value of b. Since, by assumption, the absolute value of y minus b is less than epsilon over 2 times the absolute value of b squared. And we have these facts. Then 1 over y minus 1 over b in absolute value. Combining these two fractions, getting common denominators, is just b minus y over by, all in absolute value. Therefore, this is just equal to 1 over absolute value of b times 1 over absolute value of y times the absolute value of b minus y. And again, I can just change the sign of what's inside the absolute value. So this is equal to absolute value of y minus b. 1 over y is less than 2 over the absolute value of b. Y minus b in absolute value is less than epsilon over 2 times absolute value of b squared. The absolute value of b squareds cancel. The 2's cancel. So what remains is epsilon. And so therefore, this is less than epsilon. So let's use this lemma to prove that gigantic lemma law that we proved in section 1.7. Basically, all you need to do is verify that all of the, well, one is to rewrite each of these problems in terms of something so that we can make the lemma applicable to proving what we want to prove and verifying that it really is something that we can use the lemma for. So suppose that c is a constant and the limits as x approaches a of f of x, the limit is x approaches a of g of x, both exist. Then since I really don't need epsilons and deltas, I can just state it this way, rather than having to use the notation where I specified what the individual limits were. But the limit as x approaches a, f of x was L, and the limit as x approaches a of g of x was m. I don't really need that because I'm not going to directly use the epsilons and deltas. So since I don't need to plug it into a formula, I won't use it. So first, the limit as x approaches a of f of x plus g of x is the limit as x approaches a of f of x plus a limit as x approaches a of g of x. The limit as x approaches a of f of x minus g of x is equal to the limit as x approaches a of f of x minus the limit as x approaches a of g of x. Next, the limit as x approaches a of the quantity c times f of x is equal to c times the limit as x approaches a of f of x. 4. Limit x approaches a of the quantity f of x times g of x is equal to the limit as x approaches a of f of x times the limit as x approaches a of g of x. 5. If the limit as x approaches a of g of x is not equal to 0, then the limit as x approaches a of f of x over g of x is equal to the limit as x approaches a of f of x divided by the limit as x approaches a of g of x. Oh, I guess just so that I can plug into the lemma, I guess I will actually let these limits have some sort of notation. So suppose the limit as x approaches a of f of x is equal to L, and the limit as x approaches a of g of x is equal to m. Then, given epsilon greater than 0, there exists, let delta equal the minimum of delta 1 and delta 2, where delta is greater than 0, well, delta 1 is greater than 0, such that x minus a in absolute value between 0 and delta 1 implies that f of x minus L is less than epsilon over 2, and where delta 2 greater than 0 is such that x minus a in absolute value is between 0 and delta 2 implies that g of x minus m in absolute value is less than epsilon over 2. So, since delta 1 and delta 2, let me shut my window here. Sorry. I guess they're cutting grass and the gardeners are next door and down the street are cutting grass and blowing grass everywhere. So let me close this. Okay, good. So since delta 1 and delta 2 are greater than 0, then delta is greater than 0, and x minus a in absolute value between 0 and delta implies that by lemma 1.1, we have that f of x plus g of x minus the quantity L plus m in absolute values less than epsilon. And that's what we wanted to prove. So we're done. So all you have to do is set it up so it's in the form where you can use the first part of this lemma. Next. Given epsilon greater than 0, let delta equal the minimum of delta 1 and delta 2, where delta 1 greater than 0 is such that x minus a in absolute value is between 0 and delta 1, implies that f of x minus L in absolute value is less than epsilon over 2, and where delta 2 greater than 0 is such that x minus a in absolute value is between 0 and delta 2, implies that the negative g of x minus a negative m in absolute value. Well, of course, I can just change all the signs inside the absolute value. So that's equal to the absolute value of g of x minus m, which is less than epsilon over 2. Since epsilon 1 and epsilon 2 are greater than 0, then, I'm sorry, since delta 1 and delta 2 are greater than 0, then delta is greater than 0. And x minus a in absolute value is between 0 and delta. So this implies by lemma 1.1 that f of x minus g of x minus the quantity L minus m in absolute value is less than epsilon. And that's what we wanted to prove. So you just keep plugging into the lemma, and these give you the inequalities that we wanted. Proof 3. Given epsilon greater than 0, let delta be greater than 0, be such that x minus a in absolute value is between 0 and delta, implies that f of x minus L in absolute value is less than epsilon over the quantity 2 times the quantity absolute value of a plus 1. And since c minus c, 0 in absolute value, is less than the minimum of 1 and epsilon over 2 times the quantity absolute value of L plus 1, then by lemma 1, the second part of lemma 1, we have that c f of x minus cl in absolute value is less than epsilon. And that's what you wanted to show. So we just write them in a form so that you just use the lemma. And then from there, I mean, this lemma is so chosen so that once you plug in, you get the answer. You get that whatever you wanted was less than epsilon. And therefore, proving that that limit was equal to what you wanted. Part 4. Given epsilon greater than 0, let delta equal the minimum of delta 1 and delta 2, where delta 1 greater than 0 is such that x minus a in absolute value between 0 and delta 1 implies f of x minus L in absolute value is less than the minimum of 1 and the quantity epsilon over the quantity 2 times the quantity absolute value of m plus 1. Absolute value between 0 and delta 2 implies that g of x minus m in absolute value is less than epsilon over the quantity 2 times the quantity absolute value of L plus 1. So by the second part of the lemma, we have that x minus a in absolute value between 0 and delta implies that f of x times g of x minus Lm in absolute value is less than epsilon. That's what we wanted to show. 5. Given epsilon greater than 0, there exists a delta 1 greater than 0, such that x minus a in absolute values between 0 and delta 1 implies that g of x minus m in absolute value is less than the minimum of the absolute value of m over 2 and the quantity epsilon times the absolute value of m squared divided by the quantity 4 times the quantity absolute value of L plus 1. So by the third part of the above lemma, 1 over g minus 1 over m in absolute value is less than epsilon over the quantity 2 times the quantity absolute value of L plus 1. Also, there exists a delta 2 greater than 0 such that x minus a in absolute value between 0 and delta 2 implies that f of x minus L in absolute value is less than the minimum of 1 and the quantity epsilon over epsilon times absolute value of m over the quantity 2 times the quantity 1 plus the absolute value of m. Let delta equal the minimum of delta 1 and delta 2. Since both delta 1 and delta 2 are greater than 0, then delta is greater than 0. And so by the second part of the lemma, we have that x minus a in absolute value between 0 and delta implies that f of x over g of x minus L over m in absolute value is less than epsilon. And so we're done. So we're able to prove each of those limit laws that we proved back in section 1.7 just as a consequence of the lemma. I myself am not really convinced that it's that much easier to use the lemma because it's almost as hard to put each of these in the situation where the lemma has to be used. But it is shorter. So there is a little bit of, so it is shorter, and it does show you that really we didn't, it looked like we did a whole bunch of things that were very innovative and completely different, but in reality, they were all really the same thing that we kept doing over and over and over again. So having it as one lemma so that we can just do the same, we don't have to keep doing the same thing over and over again, does have its advantages. Okay, so the other theorems really hold the same way, so I can't really improve or do them differently. So let's just list them. So I'll just list those theorems. The proofs are the same that we did in 1.7, so I'm not going to repeat the proofs because they're not different. But let me list them just so that you remember them all, so that when we do examples in just a few minutes now, we'll be able to look back or at least recall all of these. So 6. Limit x approaches a, f of x to the power n is equal to the limit as x approaches a of f of x in quantity, all raised to the power n. And this is true for any natural number exponent n. The limit as x approaches a of c is c. And so that really follows from the above limit law. The limit as x approaches a of x is equal to a. The limit as x approaches a of x to the n is a to the n for any natural number n. The limit as x approaches a of the nth root of x is the nth root of a for all natural numbers n not equal to 1, where we assume that a is greater than 0 when n is a even natural number. So that I'm not taking the square root of negative numbers. Notice that if I included 0, if a were 0, then this would have a one-sided limit, but not a two-sided limit, because you can't take the square root of negative numbers or the even root of negative numbers. 11. The limit as x approaches a of the nth root of f of x is equal to the nth root of the limit as x approaches a of f of x for all natural number exponents n not equal to 1. We'll call this the root law, where we need to assume that the limit as x approaches a of f of x is greater than 0. I don't know why I have that last statement there. Okay, so, where we need to, I see, yes. If n is an even natural number, then we would need to assume, in addition, that the limit as x approaches a of f of x is greater than 0. For odd exponents, I wouldn't need to make that assumption, but for even exponents, I would. If f is a polynomial or a rational function, and a is in the domain of f, then the limit as x approaches a of f of x is equal to f of a. And so this is the direct substitution property. How do you figure out, how you evaluate? Well, you plug in. And so how do you find a limit? You just plug in. So long as that thing that you're approaching is in your domain. So that's a very important fact. So for almost any of the examples that we're going to be doing in the next 5 minutes, the first step is direct substitution. I want to find the limit as x approaches a, just plug in a. If it's in the domain. If it's not in the domain, then we have to do something else. And this is what you do. So 13. If f of x is equal to g of x, for x not equal a, then the limit as x approaches a of f of x is equal to limit as x approaches a of g of x. Since in a limit, we don't care. Actually, this could be for all x in a deleted neighborhood of a. So if f of x is equal to g of x, and maybe I'll just sort of even specify that. So this is in for some. In a deleted neighborhood of a. Oops, let me. For some neighborhood of a. Some deleted neighborhood of a. So if f of x is equal to g of x for some deleted neighborhood of a, then the limit as x approaches a of f of x is equal to the limit as x approaches a of g of x. Since in the definition of limit, we only looked at deleted neighborhoods of a, then if they're the same, well, then the limit must be the same. And so as a consequence of this, we now have a technique. So our technique is follows. If a is in the domain of your function, then the way that you find the limit as x approaches a of f of x, you just plug in a. You find it's just equal to f of a. Otherwise, simplify. Luckily, when you simplify, the functions are equal on a deleted neighborhood. Well, if a is not in the domain and you have some rational function or polynomial function, you won't have it, then after you've simplified, the functions will be equal except at that deleted neighborhood of a, where a was not in the domain of the original function. So, technique. How do I find the limit? Plug in a. If you're dividing by 0, simplify, then plug in a. If you're able to plug in a in that simplified, then you're done. So that is the technique on how to do these limits. You basically just use these two facts. So if you have something of the form 0 over 0, after you have plugged in your a, then do more work until you can just plug in a. 14. Limit as x approaches a if f of x is equal to L, if and only if the limit as x approaches a, if and only if the right-sided limit as x approaches a of f of x is equal to L, which is equal to the left-sided limit as x approaches a of f of x. And so 15, the squeeze theorem. If f of x is less than g of x, when x is near a, except possibly at a, then the limits of f of x and g of x both exist as x approaches a. This is just the monotonicity problem. Okay. Then the limit as x approaches a of f of x is less than or equal to the limit as x approaches a of g of x. 16, here's the squeeze theorem. The limit if f of x is less than or equal to g of x, which is less than or equal to h of x, when x is near a, except possibly at a, and the limit as x approaches a of f of x is equal to the limit as x approaches a of h of x, which is L, then the limit as x approaches a of g of x is equal to L. So that's the squeeze theorem. Okay, so let's do some examples. On page 70, problems 11 through 32, evaluate the limit if it exists. So problem number 12. Limit as x approaches -3 of the quantity x squared plus 3x divided by the limit, divided by x squared minus x minus 12. So let's try to determine this limit. So this is equal to, this is equal to the limit as x approaches -3 So if I plug in -3, so the first thing to do is plug in -3. So let's plug in -3. -3 squared is 9. 3 times -3 is -9. So 9 minus 9 is 0. So the numerator is 0. Let's plug into the denominator. -3 squared is 9 minus a -3. So it's a 9 plus 3 is 12. Minus 12 is 0. So if I plug in, I get 0 over 0. And so that said to do more work. So let us factor, simplify. Let's factor the numerator. Let's factor the denominator. So I'm able to factor the numerator and denominator. Now I can cancel the x plus 3's. So this is equal to limit as x approaches -3 of x over x minus 4. So we had that one limit law that said that if f of x is equal to g of x for all x in a deleted neighborhood of a, then the limit as x approaches a of f of x is equal to limit as x approaches a of g of x. Well, if I look here, oops, this function here, and or this expression here, and this expression here, these two functions are equal so long as x is not equal to -3. So they're equal in a deleted neighborhood. Well, in every deleted, in this case, in every deleted neighborhood of -3. Therefore, the limits are equal. Note that, and this is something that even though a lot of times in previous classes they write it, this is actually not a true statement. So it turns out that these two things are not the same. So because when you plug in -3 here, it's 0 over 0, whereas you can plug in -3 here, it's a nice number. So as expressions, these are actually not the same thing. So these are actually not the same expressions, they're not the same functions, but they are equal everywhere except for one point. So when we write this, it really doesn't, we should have said actually they're not equal because they aren't. But we usually plug in equal because we say, well, they're more or less equal. They're equal at a lot of places. They're only not equal at one place. So because of that, we sort of say, well, they're close to being equal. But in a strict sense, we really shouldn't write it that, oh yes, these are equal, because they're not. But as limits, they are. So this is a true statement, that these limits are the same. Note, I say that this limit is equal to this next limit. You cannot say that this limit is equal to something that doesn't involve a limit until you've actually plugged in the limit. So I need, since this has a limit here, and I'm saying equal, then this must be, I must write that down. And similarly, this limit must be here, or I'm incorrect. But now, when I plug in -3, This is a -3 over -7, which is just 3 over 7. So my answer is that the limit is 3 over 7. Notice, I write the limit up until the time that I plug in -3 into the expression and get a result where I'm not, that makes sense. 0 over 0 doesn't make sense if I would have tried to plug in a -3 here. But 3 over 7 is a nice number. It makes sense. Any questions about that? Any questions? Okay. So notice that once we have all of these limit laws, now these problems involving limits are easy. We just plug in. We can do things now. Okay, so now let's do another problem. Problem number 18. Limit h approaches 0, 2 plus h cubed minus 8 divided by h. Again, notice that if I plug in h equals 0, 2 plus 0 is 2, 2 cubed is 8, minus 8 is 0, divided by 0, doesn't make sense. So 0 over 0, so 0, h equaling 0 is not in the domain of my function. Therefore, simplify it so that I have an equivalent, I have an expression which is equal to this original expression here, everywhere except possibly when h is 0, or at least everywhere near h equals 0, but not necessarily equal to h equals, not necessarily equal when h equals 0. Okay, so this is equal to limit as h approaches 0. Well, to simplify this, let me just expand out the 2 plus h quantity cubed. And so I'll use a special product formula, the sum of cubes formula. So let me use the sum of cubes formula. A plus b cubed is a cubed plus 3a squared b plus 3ab squared plus b cubed. So this is equal to 2 cubed, 8. Actually, let me write it as 2 cubed plus 3ab so 3 times 2 times h plus 3 darn. Let me do that over again. Sorry. A cubed plus 3a squared b. So it's 3, 2 squared, h. What I wrote before was wrong. Plus 3a b squared plus b cubed minus 8 all divided by h. Now let me simplify this. So this is equal to limit as h approaches 0, 2 cubed, 8. 3 times 2 squared, 12. 3 times 2, 6. Plus my h cubed minus my 8 all over h. Now, if I plug in 0 here, I still get 8 plus 0 plus 0 plus 0 minus 8 at 0 over 0. Okay, so I still have to keep going here. So this is equal to limit as h goes to 0. 8's cancel. So this is equal to 12. Well, h plus 6h squared plus h cubed. Each of these have a common factor of h. So let me write that. Factor that out. So 8h times 12 plus 6h plus h squared, all divided by h. Again, if I plug in h equaling 0, I get 0 times 12 divided by 0, which is still 0 over 0. Now, let me cancel the h's. Okay, so let's cancel these h's. So this is equal to limit as h approaches 0. Oops. Of 12 plus 6h plus h squared. Again, we note that each of these expressions are the same, except when h equals 0. So their limits are going to be equal. Plug in 0. 12 plus 0, 6 times 0, which is 0, plus 0 squared, which is 0, is 12. So, moral of the story. You look, see if you get something of the form 0 over 0, meaning that you're not in the domain of the function. Simplify until you can plug in. Any questions about this? Okay, let me do problem number 20. So let's do the same thing. So again, if you plug in 1, you get 1 minus 1 is 0, divided by 1 minus 1, which is 0. Simplify. And so this is difference of squares. Difference of cubes. It's still 0 over 0. Simplify. Difference of squares. Everything else is just going to remain the same. And now let's cancel. Canceling will only, these expressions, after I've canceled, will still be equal in a deleted neighborhood of 1. So this is just equal, so this is equal to t plus 1 times t squared plus 1 over t squared plus t plus 1. And so let's plug in 1. Well, if I plug in 1, I get 1 plus 1, which is 2. 1 plus 1, which is 2. 1 squared plus 1 plus 1, which is 3. And so this is equal to 4/3. Any questions about that? Okay. So this is how we try to evaluate these limits. Problem number 26. Limit t approaches 0 of 1 over t minus 1 over t squared plus t. Well, if t is 0, I'll get 1 over 0. That doesn't make any sense. Minus 1 over, well, 0 again. So I've got something that's undefined minus something else that's undefined. Certainly that's undefined. So let's try to simplify this. So I have here the limit as t approaches 0 of, well, let's factor my denominators. And so this is 1 over t plus 1. So my common denominator is t times t plus 1. So let's multiply and divide by t plus 1. Now what happened there? Okay, so I'll multiply and divide by t plus 1. And so this is equal to the limit as t approaches 0 of t plus 1 is all over the same common denominator, t times t plus 1 minus 1. So this is equal to limit as t approaches 0. The ones cancel. So I just get t over t plus 1. The t's cancel. And so I just get limit as t approaches 0 of 1 over t plus 1. And now let's just plug in 0. So when you plug in 0, you get 1 divided by 1, which is just 1. Okay. Any questions about that? Okay. If there are no questions, let's do problem 28. So again, if you plug in 2, you're going to get a 0 over 0. So let me simplify this. So this is the limit as x approaches 2. Let's factor x minus 2, x plus 2. Let's factor x squared minus 4, x plus 1. Oh, x squared plus 1. Let's simplify further. Oh, actually, I could have just canceled all those. Let's factor further. And so this is x minus 2, x plus 2, x squared plus 1. Ooh, wouldn't it be nice if I factored correctly? Sorry, I factored the numerator wrong. Okay, so luckily I found out before I plugged in. Next, let's simplify this. So let's simplify. I cancel the x minus 2's. So this is equal to limit as x approaches 2 of x minus 2 over x plus 2, x squared plus 1. And so let's plug in x equal 2. So I get a 0 over 4 times 5. Well, 0 over anything is going to be 0. 0 over any non-zero number is just going to be 0. Okay. Any questions about that? Let's do problem number 44. Problems 41 through 46. Find the limit if it exists. If the limit does not exist, explain why. Problem 44, limit as x approaches negative 2 of 2 minus the absolute value of x divided by 2 plus x. Well, before I can do this, I first gonna have to simplify this expression because it involves absolute value of x. Well, it turns out I can actually simplify this because I know what the absolute value of x looks like near x equaling negative 2. So if x is sufficiently close to x equal negative 2, meaning if x is negative, then absolute value of x is equal to x. And so the limit as x approaches negative 2 of 2 minus absolute value of x. I'm sorry, I wrote it incorrectly. Why did I write incorrectly? I don't know. The absolute value of x is equal to negative x. If you plug in like a negative 1, the absolute value of negative 1 is 1. So it's the opposite of negative 1. So it's a minus x divided by 2 plus x. So this is equal to the limit as x approaches negative 2 of 2 minus a negative x, so that's a 2 plus x. So in a deleted neighborhood of negative 2, these expressions are the same. So in a deleted neighborhood of negative 2, for x sufficiently close, but not equal to negative 2, these are equal. The x plus 2's cancel. So now, we just cancel the x plus 2's. And so we have the limit the limit as x approaches negative 2 of 1. Well, as x approaches anything, 1 just keeps a 1. So as x approaches negative 2, 1 still approaches 1. Any questions about that? So you might have to, well, just like before, you have to simplify. And so if you can't just plug in, which we couldn't, we plugged in negative 2 at the beginning, we got a 0 over 0. But if you simplified it, maybe you can actually figure out what the expression is. And we figure out what the expression was. Okay. Problem 53. So problem 53. Oh, I wonder if maybe I should. let me tell you what the greatest integer function is. So just in case you don't know what the greatest integer function. So this 1. The limit as x approaches n from the, let's see, negative. So that's from the left side of the floor of x. And the right side of the limit as x approaches n of the floor of x. For what values of a does the limit as x approaches a of the floor of x exist? So let's look at that. So let's do part A. I have here, I want to find the limit as x approaches -2 for x's greater than -2 of x. So first off, let's figure out if x is greater than -2. Well, give me some numbers that are bigger than -2. Well, let's say -1.9. So -1.9, -1.2, -1, 0. Oh, those are all numbers that are bigger than -2. So let's take the floor of each of these. And figure out what the floor is. Okay, so the floor, maybe we'll use this definition here. So the floor was any integer n where x was between n and n plus 1. So I have here the floor of x is equal to n, where x is between n and n plus 1, and it could possibly equal n. Okay, so let's look here. -1.9 is between what two integers? Well, it's between -2 and -1. And it says to let the floor equal -2. Okay, so this is -2. Now let's look at -1.2. Well, -1.2 is between what two integers? Well, it's between -2 and -1. Again, by this definition said, well, let it equal that integer. That's the floor. And so the floor is -2. Okay. Well, I'll take things at -1. Well, -1 is in between -1 and 0. It's equal to 0. Okay, so that's certainly a true statement. And so this is equal to -1. At 0, well, it equals 0. 0 is between 0 and 1. So this is just equal to 0. Okay, so let's see what's happening. So if I'm really far away, so here I am at -2. If I'm way out at 0, then the value of my function is 0. At -1, it's -1. But then when I get closer, if I'm at -1.9, it becomes -2. And if I'm here at -1.2, it's also -2. Oh, well, let's pick something that's closer, even closer. Let's say negative. Oh, I wrote that incorrectly, by the way. Let me fix this. This is a -1.2, and that's a -1.9. That's close. -1.9 is closer to -1.2 than is -1. It's closer to -2 than -1.2 is further away from it. So let's pick -1.99. If I take the floor of that, well, -1.99 is in between -2 and -1, so I let it equal -2. Oh, so if I look here, this limit is just -2. And so as x keeps getting closer and closer, it's equal to -2. So maybe what I should do is, before I even do this, maybe I should graph this. So let me graph this. So that you have some idea of what's going on. So let's sketch the graph. Let's say 1, 2, 3. Okay. -1, -2, -3. Okay, so now let's try to sketch the graph of this. So now notice that, well, let's see. If I'm in between, if I take any number, maybe I will, again, remind you of this definition here. So the floor of x is equal to n if in here is some integer, and if x is between n, and it could equal n. Oops. If x here is equal to n, if n is an integer, and if n is less than x, which is less than n plus 1. Okay, so if I look here at 2.5, 2.8, 2.9, well, it's going to always equal 2. Except when I get up to 3, in which case it will equal 3. There'll be a little hole here. Next. Well, if I'm in between 1 and 2, 1.5, etc., then it's going to equal 1. Think of it as truncation. You just got rid of, so it was 5.1. So I just got rid of the 0.1, 4.99. I just got rid of the 0.99. Okay, so between 0 and 1, well, it looks like this. Now, if it's less than 0, it has to have the same pattern. So it's not really going to be this truncation for the negatives, but it'll follow the same pattern. So it will go from here to here. It'll be -2, -3. So it'll keep following the same pattern, okay? And it keeps going. Okay, so now we can, looking at this sort of as a cheat. So now that we've done all this sort of cheating work here, meaning we've drawn the graph, now I can use this graph to help me find the limits, because now it's a picture. And so this picture will help me to figure out what's going on. Okay, so let's find the limit here. As x approaches -2. As x approaches -2 from the right. So I'll just look at the picture. So I'm approaching here -2. So I'm approaching the -2 here. Oops. So I'm approaching this -2 from the right. So I'm coming from this side. Well, for every value on this side, my function just looks like it's always equal to -2. Therefore, the limit must equal -2, because for all values of x near -2, but greater than -2, the floor is equal to -2. So therefore, the limit is -2. And you're done. Let me do part 2 of this. So that was part 1. Oops. Was it called A or part 1? Oh, it was called A part I. Oh, okay. So this is A part I. Okay. So now let's do part 2 of A. So part 2 of A says to find the limit as x approaches -2. So I now want to find the two-sided limit. So let's try to determine my two-sided limit. And so I have here -2. I want to approach from both the right and from the left. As I approach from the right, well, the values are always -2. As I approach from the left, the y values are always -3. So one-sided limit, the right-sided limit, approaches -2. The other side limit, the left-sided limit, approaches -3. Therefore, since these two limits are not equal, then the two-sided limit does not exist. So my two-sided limit does not exist. Let me do part 3. Find the limit as x approaches -2.4 of the floor. Okay, so let's look back up here. So we want to approach negative 2.4. So negative 2.4 is somewhere around here. So I want to approach it from both sides, this way and this way. Well, notice at 2.4, my y values are negative 3. Near 2.4, all my y values are negative 3. Therefore, the limit as x approaches negative 2.4 is negative 3. Let's do part B. I. Okay, so part 1 of B. So for part 1 of B, I want to determine the limit as x approaches n for some integer n, and I want to approach it from the right side. Okay, so let's approach from the right side. So I'm going to approach this way. Okay, so let's see if I'm approaching 3 from the right side. Oh, I'm sorry, from the left side. It's negative, so it's from the left side. So if I'm approaching 3 here from the left side, notice my y values are always equal to 2. So this is just equal to 2. If I approach from the left side, I'm approaching 2, the y value is always 1. So it's always going to be 1 less. If I approach the y, if I approach negative 2, then I'll get negative 1, negative 2. Then I'll get negative 3. Okay. And so it's always going to be 1 less. And so the limit as x approaches, so the left side limit as x approaches n of the floor of x is just equal to n minus 1. And that's your answer. Let's do part 2. So for part 2, I want to find the limit as x approaches n from the right side. Well, if I approach 3 from the right, then my y values are always equal to 3. If I approach 2 from the right, the y values are always 2. Approach 1, y values are 1. Approach 0, y values are 0. Approach negative 1, y values are always negative 1. So this is just equal to n. Okay. So lastly, it just says part C. So part C. For what values of A does this limit exist? The limit as x approaches A, the two-sided limit. When does the two-sided limit exist? Well, oops. Notice that if it were at any integer value, if I look here and I take an integer value, it's not continuous. There's these jumps. At all integer values, there are these jumps. But if I'm not at an integer value, then notice that it always has the same value near these non-integer values. And so this will be continuous everywhere. The limits will exist everywhere except at integer values. So it's everywhere except at integer values. Any questions about that? Okay. So that finishes off section 1.6. So let me give you guys a 10-minute break up until 9:55. So at 9:55, we already did section 1.7. So we'll go on to section 1.8, which is on continuous functions, continuity.